Hi, in this video, I'll be talking about the extended real number system. So, in the previous 8 videos, we have went through a lot about sequences in the real numbers. What are the real numbers? And we now understand better of how the real numbers works. But then we need to tie up some loose ends, and so this video will cover the extended real number system, where now it is just the real number system, but you have 2 points, and these 2 points are labeled infinity and minus infinity, and they just represent points or elements that are greater than all real number system for infinity and less than all real number system for minus infinity. And because of that, we can actually just, it now forms a total ordered set. Because infinity is an expression, it doesn't have an inverse. You can't really do operations on them. You can't say that this extended real number system is a field, but you can still say it is a total ordered set. And because it's an ordered set, you can talk about the sup and the inf. And what's more is that you can actually say that this sup and inf always exist in the extended real number system. So really, it's just a way for helping us to talk about sums and infs easier, basically, because now you know they always exist. And it gives us points so that when we can now say when a sequence tends to infinity. And so it tends to infinity if there exists a natural number k such that n larger than k, xn will be larger than a for every real number. So because you know it tends to infinity, it must increase all the way to infinity. So for every real number, there will exist a cutoff such that all the terms after that is greater than this real number. And it tends to minus infinity if for every real number, now xn is less than beta for some cutoff. And really, this tending to infinity, we say that it's properly divergent. Or you can just say that it converges to infinity. So, like the warning over here, you should just realize that this plus and minus infinity are just notations for expressions that we want to convey to say that it's larger than all real numbers or less than any real number. And so we can characterize being properly divergent or converging to infinity by saying that it is converging to infinity if and only if it's unbounded. And if it's increasing unbounded sequence, then it's converging to infinity. And if it's the unbounded decreasing sequence, then it converges to minus infinity. So let's prove it. So we suppose that xn is an increasing sequence. And we know that xn is bounded. Then it is convergent. So if it's unbounded, then there will exist a cutoff such that for all x beyond this cutoff, it will be larger than alpha. And since xn is increasing, all the xn's larger than this little na will be larger than alpha. And since alpha is arbitrary, this proves that the limit will go to infinity. And similarly for b, for decreasing. And so this shows that if you are bounded, then you're convergent. And if you're unbounded, then you just go to converging to infinity. And we're done. So a corollary of this is that for any sequence now in the real numbers, you can find a subsequence that converge in the extended real number sequence. And what do I mean by converge in the extended real numbers is because it can converge to a real number or it can converge to plus minus infinity. So we can still say it converges, but now in only the extended real number sequence. So what we like to now say that if we have two sequences and it satisfy, and one sequence is always greater than the other sequence, if we know the smaller sequence converge to infinity, then the large sequence y must also converge to infinity. Likewise, if y converges to minus infinity, then x also converges to minus infinity. And I hope the proof is very clear, and really you can make use of the fact that if y is greater than xn and xn converges to infinity, it means xn is unbounded, and so yn is unbounded, and thus yn converges to infinity. So you can prove it similarly for part B, and I won't go through that, but you can also read the textbook for the answer. Next, we shall prove that if a sequence has a limit that approaches L, so the sequence is made of xn divided by yn, then the limit of xn being infinity will only occur if and only if yn limits is also infinity. So you can just think about it that if this property of being a limit equals to L, then there will exist a cutoff such that this sequence xn over yn is bounded between half L and 3 over 2L. And so this means that half L times yn is xn is bounded between half L times yn and 3 over 2L times yn for all n larger than k. And so we just need to modify what we have said in here, because now if xn goes to infinity, then yn goes to infinity. And if yn goes to infinity, then this part is infinity, and so xn goes to infinity. And so you can just play around with this theorem, and then you have actually proven the result. But of course, this L must be greater than 0 and a real number. And so you can find examples to show that if L equals to 0 or L is not a real number, it won't happen. And so really the last proposition that we shall prove in this video is that we want to show when a sequence actually converges in the extended real number sequence. And instead of just saying that it does converge, we want to characterize it. And so the characterization is this. It has the property that for all a's less than this limit, there will be infinitely many points in the sequence larger than a. And for all points, and for anything greater than the limit, there will exist a point such that all the xn's are less than this b. So you can just think of a as over here, x over here, and b over here. All your points now must be trapped within this interval. And for the cases of infinity, this you can see that it holds true by definition, so I won't go through that. But really what we want to say is that what if this is a real number? And if that's a real number, then if a is minus infinity, we can just choose any of the n's and it will work. And if a is a real number less than x, then we can take epsilon to be x minus a, and xn converging to x. The convergence of xn will imply that there is a cutoff such that x minus xn is less than epsilon, and this epsilon is x minus a. And so this will imply that xn is greater than a. And so you have shown this part. Now we want to show the next part. So you just take b to be greater than x, and then you can just do the same idea. Because xn converges, you can now do it xn minus x being less than b minus x. And if b is infinity, then you can just take n to also equals to any number and it will work. So you have proven the forward direction, where if this is convergent, you know these two properties holds. Now we want to use these two properties to prove that xn converges. And so given an epsilon, we just take a to be x minus epsilon and b to be x plus epsilon. Then by the earlier proposition, there will exist a cutoff n1 and n2. And so you just take the maximum of this cutoff, and then xn will be bounded between a and b, which means it will be bounded between x minus epsilon and x plus epsilon. And so xn is bounded between epsilon so xn minus x is bounded between epsilon. And this, because epsilon is arbitrary, xn converges to x. And we are done. And so this gives us a formulation or characterization of when a sequence converges in the extended real number system that we can use usefully, because now we can talk about the terms in the sequence. So that's all for this video. I hope you've enjoyed it. In the next video, we shall just wrap up the idea of sequences with limit sup and lim inf, or also known as upper limit and lower limit. So I'll catch you in the next one. Bye.